This is me, Matt Jarvis. I work at a company called Mesosphere in San Francisco. Mesosphere builds software to orchestrate clusters, and that's kind of what I'm going to be talking about in this talk today. You know, I've been around open source software for a pretty long time, as you can probably tell from the gray hair. And I've worked in development of distributed systems and in operating these things, so I've seen quite a few trends come and go over the last few years. I'm going to start with a bit of setting the scene. I'm going to play a little fast and loose with the history of computing in the interests of telling a better story, so please feel free to come and hit me afterwards. So in the beginning there was batch processing. Mainframes like this fine IBM model, running single workloads to start with. And you know, in that model we got very high utilization rates. We can generally choose when we're going to schedule, when to run things, so allowing for shifting workloads to quieter times. And the basic idea of this is that we take a bunch of data, we do some stuff to it, we return the results, and rinse and repeat. And so it's very transactional, very well defined. And what that looks like from an application perspective is this highly monolithic stack where we have hardware, we have an operating system running on that hardware, and we have a single application that operating system is designed to run. And as we move through the mini-computer era to the workstation, that pattern remained fairly similar. The machines to do it got a bit smaller, the I/O got a bit quicker, the storage got a little bit bigger, not much bigger in comparison to today's machines. And in the 70s and 80s, we start to see this emergence of this client-server model, a little machine or lots of little machines talking to a big machine. But again, the processing paradigms that we're talking about there weren't really that different. In general, we're still taking some data, running processing against that data on a single machine inside a single box. Or we might push those results somewhere else, or we might pull our starting data from somewhere, but fundamentally, we're still within that single box. And then in the late 90s and early 2000s, we start to have this very massive growth in the internet. And in order to deal with this unprecedented transactional volume, the early web-scale companies start to build these huge fleets of off-the-shelf hardware. And the major problem that all of those companies were facing was how to make most efficient use of those computing clusters. And so we started to see some fairly big paradigm shifts in application architecture that are pretty familiar to most of us these days. And one of those new approaches was MapReduce, programming technique for distributed systems, which splits tasks into two phases. And then we spread that out across the cluster, operate on the smaller bits, and pull it all together at the end. And that originated from inside Google, and then was generalized most famously into things like Hadoop. And so now we could all parallelize processing operations across big clusters of servers. But even in this model, we're still performing effectively a batch operation. And the issue with that first generation is that we were dedicating computing resources to each of these single frameworks. So we subdivide our fleet into various silos, and those silos are all doing one particular kind of work. And this is generally pretty inefficient in terms of resource utilization. And we have a problem where when we lose machines out of those individual silos, it's very difficult for us to manage around failure. So we end up over-provisioning to deal with both peaks and troughs and to deal with failure scenarios. And the other problem with static partitioning like that is that workloads are almost never uniform in either time or resources. So we have certain workloads that may be long running but not take much resource, but we have other workloads that are highly spiky, and we have some that are very short-lived. And again, we have to over-provision to deal with those patterns. A much better approach would be to dynamically share resources across our entire cluster, which would give us much higher utilization and a much more efficient use of all of our machines. And around the same time, we start to see the kind of big wave of virtualization. And virtualization is not really that new a technology. And I mean, in some ways, you could say it's been around since the mainframe era. But around that kind of time, we have a very big growth in virtualization, and we're all familiar with what virtualization looks like. We have a hardware platform, we have a hypervisor, and then we have a bunch of virtual machines that are running on those on that hypervisor. And what that does to us conceptually is we now have many, many more machines that we can run. And we can more efficiently use those hardware resources, but we also add complexity. We have a lot more machines to manage. We have a lot more operating systems. We have a lot more applications. And that kind of, that split in the infrastructure layer led us to start to subdivide our applications into smaller and smaller units, the kind of rise of microservices, matching that subdivision at the infrastructure layer. And microservices, we know, were all designed to be these small autonomous things that work together, doing one thing and doing that one thing well. And now we've added that complexity. The microservices stuff gives us those benefits of being able to scale our applications more efficiently. But what it also does is cause us further problems. Because now when we look at our application stack, we have our virtual machines, we have our operating system running on the virtual machines, and then we have many more applications running inside those operating systems. If we start to make any changes to that operating system, those applications are all relying on the same libraries. And that's potentially going to cause problems when we make changes to one or many of those applications running on our machines. So it's very difficult to manage, and we've got a lot of problems with dependencies. And so in the last few years, we've started to see widespread adoption of container technology. And again, container technology for anyone who's been around in the Unix world for very long, those container-like technologies have been around for probably 20 years or so. But we've started to see very widespread adoption of that. And, it's probably important to differentiate here between the idea of a container as a packaging format and the process of containerization by which an application maintains process isolation. And the process by which the application remains isolated are actually all functions of the Linux kernel. Containers are not a thing is a very famous quote these days. They're just a bunch of stuff that happens in the kernel. And, lots of people get confused between the packaging formats like Docker and what's actually happening there at the operating system level. But, the rise of Docker really standardized the idea of a packaging format. And that's very important because we end up moving from that scenario where we've got dependencies on system libraries to a scenario where now our applications are packaged together with all their dependencies. And so we can deploy on top of our container runtime all of our applications, and they're not relying on things that are in the operating system. So we can change stuff in there, and nothing's going to happen to our applications in theory. When we first started using containers, I think that there was a bit of an uphill struggle for people to get their heads around the best patterns of how we use these things. Lots of people were like, how do I shell into my container? How do I update things in it? And I think we're now reaching the point where people have accepted the idea that the best part of containers is that they're immutable. So when we create them, we never change them. If we want to update our container, we rebuild it, we kill the running ones, and we start replacement ones that have our changes in them. And so at this point, we've got a whole bunch of benefits from containers. We can deploy them really rapidly. They start up very fast. We've kind of solved our dependency problems somewhat in that we're now packaging all of our libraries and dependencies together with our application. And we get benefits of things like image repositories, so we don't need to create everything from scratch because we can pull stuff in from repositories, we can build on other people's work. But the big problem at this point becomes how do we schedule our containers across our whole fleet? How do we know where they are? How do we connect them together? And what happens if a machine dies? And so the solution to those problems is the idea of container orchestration. An overlying system that handles where we place containers, handles a lot of the underlying plumbing. And whilst this introduces a lot of capabilities to us, it also introduces a lot of complexity. And so what container orchestrators generally consist of is these kind of three pillars. We have container scheduling, we have resource management, and we have service management. So from the scheduling side, orchestrators generally are keeping track of where we place individual containers. How do we scale our applications horizontally? How do we resurrect things if things die? And how do we do upgrades and all that kind of stuff? And then from the resource management side, we are interested in our overall resource utilization across our fleet. How do we allocate that most effectively? And that can be, hardware stuff like memory and CPU, but also things like IP addresses and ports and other artifacts we might need to run our containers. And then on the service management side, this is about connections between things. So which things need to run before other things? How do we tell whether a service is ready or not for things to connect to it? And how do we group things together? And so once we add that container orchestrator layer, it really abstracts away all of the stuff at the bottom. So right from all of our machine infrastructure, all of our container runtimes, our operating systems are all abstracted away. And we're just left with our container orchestration layer that treats our underlying infrastructure as just pools of resources where applications can be deployed. But that doesn't really solve all of our problems because in the last few years, we've seen emergence of new classes of applications, which are not just about containerized microservices. And these new architectures look much more like pipelines than that traditional batch computing paradigm that we looked at earlier. We have events being generated by something. We might have something ingesting those events. We probably want to do some analysis on that data. We may want to store it persistently. And we probably want to do something with the results, whether that's visualizing it or triggering other actions. And there's a bunch of things happening in enterprises that are really driving these kind of architectures. Things like real-time advertising, which we're all familiar with. The instant you look at something on Google, you're then bombarded by adverts for it. In financial services, detecting fraud very quickly in things like credit card transactions. And then the rise of things like Internet of Things, where many, many more producers of data. And one of the really common patterns that we at Mesosphere see for this kind of pipeline is what people have talked about as the SMAC stack. This an acronym, stands for Spark, Mesos, Akka, Cassandra, and Kafka. And we'll come back to Mesos in a minute. But those other applications are all part of a class of cloud-native applications developed specifically for this kind of fast data world. Many of them were developed inside big web-scale companies and then open-sourced, and so now they're available to all of us. Despite that acronym, there are actually a ton of different variations on this, but they all map fairly neatly onto that pipeline paradigm with a bunch of microservices to kind of interact with the different tools. Now, all of those applications are complex distributed systems in themselves. So the requirement for deploying and operating those systems are becoming increasingly complex. They all have different requirements for placement, about data locality. Where do I need to be? How do I need to be close to my storage? How do I scale? How do I upgrade? And we're still trying to maintain maximum efficiency in terms of resource utilization across that entire fleet of hardware. And one of the most mature approaches to this problem, and one that's particularly well suited to that idea of running multiple distributed systems within a single substrate, is Apache Mesos. And you can think of Mesos as a distributed kernel. So a lot like the Linux kernel, it's responsible for low-level task scheduling. But you can also think of it as a distributed system for running other distributed systems. Mesos is massively scalable and battle-hardened in production to multiple tens of thousands of nodes. And it's in production at some of the world's biggest internet services. So if you've used Twitter, if you've used Netflix, if you've used Yelp, then at some point your interaction with those services has passed through Mesos. To talk a little bit about the history of Mesos. So Mesos was started out life as a research project at the University of California, Berkeley. The original team who wrote Mesos also wrote Apache Spark as a example framework for running on top of Mesos. Ben Heinemann, who's one of the founders of Mesosphere, had friends who were working at Twitter, and he went into to Twitter to give a talk about Mesos. And at the time, Twitter were experiencing a lot of scaling problems. For those of you old enough to remember, you may remember this image, the fail whale, which Twitter used to put up on their website whenever the service went down. And this was a very regular sight on Twitter's site during the early years of them scaling. And so Twitter eventually decided to implement Mesos, and really that's why you don't see that fail whale anymore. That research group then published a pretty famous distributed systems paper about Mesos, and Mesos then went into the Apache Foundation as an Apache project. And Mesos is under the governance of the Apache Foundation, so there are many different contributors to the Mesos source code, and a bit further down the line, Ben and a couple of his friends started Mesosphere to actually build a project on top of Mesos to make Mesos easier to use, which we'll talk about in a second. And so the other interesting thing to point out is that, in this world of large-scale cluster orchestration, Mesos was kind of building on stuff that did exist, ideas that had already existed inside some of the really big web-scale companies. Some of those companies who I said at the start were the first ones to really struggle with this concept of how do I make most efficient use of very large computing clusters. So inside Google and Facebook, there had been work done already, but in a proprietary sense, and the original Mesos group were in touch with those folks as well about the best way to overcome some of the challenges that both Google and Facebook had seen with trying to build these kind of systems. So back to Mesos. The key differentiator between Mesos and all other kind of cluster orchestration systems is that Mesos has this concept of two-level scheduling. And I'll talk about that in a second. I'll just talk through what the base architecture of what a Mesos cluster looks like. So we have a Zookeeper cluster. The Zookeeper cluster is there to handle election of masters. It's also there to do some small key value stuff, but it's mainly used for Paxos selection of masters. We'll then have a number of masters, normally in an odd number, so that we avoid the problem of split braining in the cluster if we lose master nodes. And one of those master nodes is elected as the leader. And then we'll have a number of slaves. These are actually called agents in modern parlance. This image is slightly old. And those slaves will effectively be all of your hardware will be running those slave processes. And the only thing that the master really cares about is making offers to what Mesos calls frameworks, which are effectively other applications. And a framework has its own scheduler. So the Mesos master is not deciding where to place workloads. All the Mesos master is doing is saying, I have this resource available, do you want it? And this is a concept called non-monolithic scheduling, and in distributed systems, it's pretty much validated as the way to scale to very big cluster sizes, because the master doesn't need to know about the placement of every single workload on the cluster. So a framework has a scheduler, and it has executors, and executors run on the agents at the bottom on your actual hardware, and those executors are tasked with actually doing work. So if I need to spawn a particular process from a framework, that's what the executor will do. And that communication all happens through the master. So the framework scheduler will accept a resource offer and then cause that executor to actually execute a task. And so what does that mean for our data center in a very broad brush sense is that, this is a slightly different view of that static partitioning on the left, where we see, single machines or groups of machines allocated to a particular workload. What happens in Mesos is that those workloads are multiplexed together onto individual machines. And so we get much higher density. And those processes are isolated from each other, sometimes in a Docker container sense, but in other ways, just by Mesos natively handling the stuff in the kernel to separate out those processes. Mesos actually predates Docker, so Mesos has its own concept of containerizers, which we'll talk about in a second. So Mesos is primarily API-driven, does have a UI, but as you can see, it's not massively user-friendly. It's a bunch of UIDs and stuff. I can't really tell what's going on in my cluster. And there's a bunch of things that we'll come on to later that Mesos doesn't give you natively. And we don't really have much real insight there. And for the same reasons that Mesos is that powerful abstraction, it's also pretty complicated to use in production. And there are a bunch of stuff that you need to scaffold on top of it in order to give you that full scope of what we expect from modern cluster orchestrators in terms of operational stuff like monitoring and logging, and deployment automation, service discovery, load balancing, all that kind of stuff. And most of those early web scale users developed their own systems in-house on top of Mesos. But Mesosphere was really formed to kind of democratize that, so that companies and users who didn't have access to a team of 100 engineers just to work on the scaffold around Mesos to be able to have something to use. And so DCOS, which stands for Data Center Operating System, is basically a distribution of Mesos, along with a UI, a CLI, and all the bits that you need to run Mesos in production environments, monitoring, security. And most importantly, a catalog of pre-configured applications. And by applications, I mean services/frameworks that are encoding best operational practice for these distributed systems that run on top of DCOS, and we'll talk about that in a second. So DCOS is an open source project. Mesosphere do have an enterprise version, adds some stuff that enterprises tend to care about, like integration with enterprise auth systems and some additional security features, a deeper RBAC. But the open source project is fully functional. It's all the things are available for you to use there. It's not limited in any way. And it's basically an umbrella project for a whole bunch of other stuff, around 30 different open source projects. So when we look at DCOS from an architecture perspective, this is kind of what it looks like. So we've got Mesos at that bottom layer. And then on top of Mesos, as I said, we've got some native container orchestration, which we'll talk about in a minute, a whole bunch of security features, monitoring and operations, and then ways for you to interact with the system, so the UI, the CLI, the API. And then at the top, we have our catalog of applications that are super easy to deploy. And then we can run DCOS pretty much anywhere. So it runs on bare metal, on virtual machines. You can run it on private cloud, and it'll run on your public cloud provider of choice. We generally see about 60, 70% of DCOS users are really about running this on-prem because it gives you that kind of public cloud flexibility without actually being in public cloud. In the enterprise project, there's actually a whole bunch of hybrid cloud features where you can do cloud bursting and all that kind of stuff, but I'm not going to talk about that. So from a UI perspective, we could see straight away that DCOS gives us a much clearer picture of what's going on in our cluster. It's much more focused on the operational things that we need to see whether what we're trying to do is working correctly. So we can see in this view, we've got the health of the applications that are running within our cluster. And you've through the CLI and API, you've got access to all of the functionality, so it's very easy to automate, very easy to integrate with. And so the catalog, which is one of the key kind of functions of DCOS, is I think up to I think there's 50 or 60 applications pre-packaged in there, and that we have this distinction between certified and community. So the certified ones are in the Mesosphere QA chain, so we're testing those, but there are a whole bunch of other stuff in there that's submitted by the community. In most cases, the complex things like Kafka and Elastic and stuff, the folks who are building and maintaining those packages are actually the creators of that software. So when you deploy something like Kafka from within DCOS, then it'll give you straight away a working clustered version of that particular application. And we can deploy in a number of ways. We can do it just through the UI. In most cases, we can accept the defaults, and you're going to have something that's going to work straight out of the box. Nothing's hidden from you. All of the configuration elements, even within the UI, are available to you to change, and it's literally just a case of clicking a button. But in general, more people are more likely to deploy things programmatically using the CLI. So we can define JSON like this, and then we can run a single command, DCOS package install our application name with options to give it a config file and deploy applications like that. And coming back to the idea that I said earlier about these aren't applications in the typical sense that we might install a package in our operating system, because most of these applications have their own framework scheduler, and the framework scheduler is doing more than just unpacking the application. It's actively managing the life cycle of that application. So if we lose an element and lose a particular piece of that application, then it's going to be respawned, and we can have a look at some of the things that typically an application package will provide through using this plan list the command, and generally these services that are built using using our SDK have this plan command, which will show you the typical kind of operational things that the framework scheduler can do if you need to. So it's typically things like scaling, like upgrading, or recovering from a hardware failure. And when we look a bit deeper into the plan, these are all from the Kubernetes package that is in the catalog. We can look at the ordering that the scheduler will use in order to do a particular task. So this is the deployment of Kubernetes. It's cut off at the bottom because this is a huge, long thing here. But we can see that it knows about the order that it needs to do things in. So when we deploy a Kubernetes cluster, it knows that it needs to bring up an etcd cluster to start with. It can only do the etcd part serially because the etcd cluster needs to actually talk to each other. But then we can also see that it knows that certain elements of this plan it can do in parallel. So it's encoding all of these things, this operational knowledge of how you might do particular tasks. So when we're dealing with orchestration systems, one of the most critical elements is service discovery. We might have lots of machines, we might have lots of applications. How do we know where our applications are? Particularly when we're working in environments where IPs and ports may be dynamically allocated, so they can be pretty much anything, and our actual services themselves may be dynamically changing. So if we lose a particular node, those containers may be respawned somewhere else. And so it's very difficult in this picture here for us to know, how does my client application know where my service applications are? And so the typical model for how we manage this is service discovery. So when our services start up, they will register with some central registry mechanism, and we might have something like a load balancer, which is querying that registry and updating itself all the time as those particular elements of that application change. And so then our client only needs to know about where our load balancer is, and it doesn't really care about where any of these services happen to be at a particular point in time. And in DCOS, we have two mechanisms for service discovery. The first one is called Mesos DNS. And as the name suggests, it's DNS-based. So every element of every application, every task that Mesos spawns gets allocated a DNS entry in this particular format. And clearly, when you have multiple instances of a particular service, you're going to get some basic round-robin load balancing there. But the complexity here is that we need to know the port of that particular task or container may be running on. And so any application that wants to use Mesos DNS to resolve things needs to know not only how to look up an A record, which pretty much everything does, but how to look up an SRV record for that to get that port. Depending on your DNS configuration, DNS can also be slow to update. So if we've got very dynamic environments, that might be somewhat of a downside. So the second mechanism is this mechanism called named VIPs. And this allocates this name-based virtual IP, this very long string here. And this is integrated directly with the Linux kernel, with the connection tracking table in the Linux kernel using IPVS. And it gossips between the agents so that they're all constantly updated about where particular things are living. So this gives us very fast update times, somewhere in the region of 100 milliseconds. And it provides east-west load balancing, i.e. inside our cluster. And the other key mechanism we need is load balancing. So when in microservices architectures, typically a service is going to be made up of a whole bunch of different things. We need something that's going to sit in front of those things and direct that traffic. The basic load balancer in DCOS is called Marathon LB. Marathon LB is based on HA proxy. I'm sure many in this room are familiar with HA proxy. It's pretty much industrial strength, open source load balancer. And in Marathon LB's case, it's integrated directly with the configuration of the system. So if you've configured your app to use Marathon LB, then when instances are spawned or go away, they will be automatically added or removed from the Marathon LB configuration. And this Marathon LB can be north-south, so it can be traffic coming in and out of your cluster, or you can use it east-west inside for applications to talk to other applications. So storage is probably one of the most controversial areas, I guess, in containers right now. Containers work very well for stateless services, where we don't care about any state that container happens to have. If it blows away, then we just start another one. But the reality is that most services are not stateless. Even when we hope they might be, lots of things turn out to really care about state. Even in some of the cloud-native frameworks where we've got replication between nodes, people might choose to make them stateful in order to avoid long recovery times by things moving about. So, as I'm sure some of you are aware, there is an emerging standard in this space, the container storage interface, and Mesosphere are part of the core team developing that, and that's integrated into the latest release of DCOS. And we kind of have three other mechanisms for doing storage for containers. Clearly stateless, that we just allocate a bit of the file system for a particular container, and that's blown away when we lose that container. Mesos can do local persistent storage. So you can allocate a drive or a part of a drive to a particular container, and that's going to work okay if we lose the container, but clearly if we lose the agent that persistent volume's hosted on, then that's not going to be great. You can integrate with Rexray, which is a Dell EMC thing. I'm not quite sure what the current maintenance state of Rexray is, but that enables you to integrate with external storage, things like SANs. And there are also a bunch of kind of pretty popular third-party things. Portworx is one that's particularly, we see a particularly large bunch of users for. And those give you persistent distributed volumes across your cluster, so you don't need to worry about losing individual agents. In Portworx, they're actually distributed all across your cluster. And networking, again, is kind of a little bit of a difficult topic, I guess. You know, everyone wants to do networking in different ways. Everyone's got opinions on which way they think things should be hooked up together. From the DCOS perspective, our position is to be as unopinionated as possible and to let people plug whatever they want in. And so whilst we do have integrated VXLAN-based virtual networks, so you can have basic layer 2 separation on the wire, we support the container network interface standards. So if you want to plug in things like Calico or OpenContrail, then that's you can do that, and they just use CNI. So lots of people make the comparison between Mesos and Kubernetes, and it's really the wrong level to make that comparison at. Mesos operates at a lower level than Kubernetes does, as hopefully has become clear from this talk. Marathon is the native container orchestrator that ships with DCIS, and you can probably think that Marathon is analogous to Kubernetes as opposed to Mesos being. So Marathon handles all the requirements for spawning containerized microservices onto DCOS agents. It supports a whole bunch of stuff like pods, GPUs, health checking, and if things die, Marathon will restart them. And Marathon's basic job is whatever you tell it to do in terms of an application, it's going to try its best to make sure that that pattern that you've defined is going to continue to exist. So most people are more familiar with in the container kind of terminology with running Docker containers, and so DCOS provides a whole range of ways that we can just basically run Docker containers. We support Mesos has this concept of different containerizers, and again, this is because of predating some of the newer stuff that Mesos has always had the idea that you could plug in different ways of containerizing applications. And so the first way that you can run Docker containers is using the Docker containerizer, which effectively runs Docker natively on each of the agents. And so when something like Marathon wants to run a Docker container, it will hand that straight over to the Docker runtime, and the Docker runtime will handle all the stuff about actually running those containers. One of the problems that we saw particularly at scale was problems with the Docker engine, and so the Mesos native containerizer was been extended to this thing called the Universal Container Runtime. So that you don't need to actually run Docker on that layer at all. Using UCR, UCR understands all the stuff about how Docker containers work natively. So it understands Docker registries, it understands the Docker container format, and so we can spawn Docker containers natively without using Docker at all. And then we've also added Kubernetes as a framework natively running on Mesos. And really that's about abstracting away all the operational complexity of running Kubernetes. If you look at something like Kelsey Hightower's Kubernetes the hard way, you've got something like 20 plus discrete steps for how you actually deploy a Kubernetes cluster. And one of the emerging patterns in Kubernetes is that people are running lots and lots of clusters because I think Kubernetes work, because the Kubernetes scheduler actually keeps track of where all the applications are as well. The idea that you could run very, very, very large single Kubernetes clusters is never going to work. So we see lots of users who have tens or even hundreds of individual Kubernetes clusters. So if we can imagine that from an operational perspective, how do we deploy and manage all of those different Kubernetes clusters? You can imagine that it's extremely complex. Even if we're using config management or whatever to deploy them, that's still a whole ton of code that you've got to manage, you've got to update. So with the Kubernetes framework in DCOS, it's a single CLI command to install a highly available Kubernetes cluster. As I said before, if we lose elements of that, we do demos where we go in and actually kill individual kubelets, kill etcd peers, and the framework knows that it needs to have those running, so it's going to restart them. It's unmodified Kubernetes upstream, so I think we're aiming to be something like 2 weeks behind each of the Kubernetes releases in terms of upgrading the framework. And there's no extra patches or anything, it's completely unmodified. So you interact with Kubernetes on DCOS exactly as how you would interact with Kubernetes anywhere. So kubectl and all that kind of stuff is exactly the same. We expose the API endpoints directly. So coming back to some of the operational features, this is a different view of the DCOS dashboard, and I think this one kind of gives you a better picture of like how you can see the entire operation of your fleet from one particular pane of glass. And this is the whole idea, is simplifying this operational view across all of this complexity. So from this view, we can see all of our resources. That's all of our resources in our entire cluster. We can see what tasks we've got running. We can see what's the state of individual components within the DCOS cluster itself, and what's the state of the services that we have running in the DCOS cluster. And there are a few other things that we provide in order to simplify that operational complexity. The first one is that the frameworks will generally have integration with the DCOS CLI and UI, so that rather than having to switch out between different CLIs to achieve common operational tasks, we'll have for example, a CLI extension where we can just use the DCOS CLI in order to do that stuff. So this is an example of very familiar, I'm sure, to anybody who's used Kafka, of creating a topic in Kafka, right? So instead of switching to the Kafka CLI, the DCOS CLI all configures itself, and you can just use the DCOS CLI to do a lot of that operational stuff. And then where we might have web interfaces that are provided by a particular framework, particular application that we've deployed into our cluster, we will generally make those frameworks available, those UIs available from the DCOS UI. So there'll be a little hover button next to that service. You can click that button, and that UI for that service will spin up. And that's done by proxying those things through what we call the admin router, which is a proxy that allows us to do traffic into the cluster, because obviously those things are deployed inside our cluster, and as a user we may not have direct access to them. From a log perspective, all of the logs for any task that's running on our cluster are all aggregated. They're available via the UI, the API, or the CLI. And there's what we see in general as a pattern is that people want to integrate with things like Elk upstream, with the Elasticsearch Logstash and Kibana. And so those logs are all available as files on the disk, so that you can run something like Filebeat and just pick up every single task that's running within your cluster. And then from the API, we've got the logs endpoint, and from the CLI, you can do a bunch of stuff. There's a ton more of these, but this is just to give you an idea. If we want to see the log of an individual task, we can just use the DCOS task log, or if we want to see the logs of a particular node, we can use the ID of that node and get all of those logs from a single command. And metrics is a pretty similar story. So again, everything's aggregated and available through all of those mechanisms. Custom applications can publish their own custom metrics into the metrics API using a statsd endpoint that's available to all containers. And we have native Prometheus endpoints on each agent, so you don't need to install any additional Prometheus stuff to make that work. And in fact, if you deploy Prometheus from the catalog into your DCOS cluster, it'll pre-configure itself to pick up all the Prometheus endpoints that you've got running in that cluster. So it's literally, that will set you up and you're good to go. So kind of coming to the end, there's a bunch of ways that you can try it out if this has been something that you might be interested in. We have a DCOS Vagrant project in GitHub, so you can spin it up in Vagrant. There's a DCOS Docker project as well, where you can spin it up locally in Docker. And there are automation scripts for all of your cloud platforms of choice. There's a bunch of ways that you can interact with our community. So DCOS.io is our community website. We have a very active Slack community, chat.dcos.io. There's a whole bunch of stuff you can look at on GitHub. And I'm happy to take any questions.
We have still some time left.
Does DCOS support multiple tenants? Does it have a model?
So in the enterprise version will have multi-tenancy. The open source version at the minute is single tenant from that perspective. In the enterprise version currently has very sophisticated RBAC, so that you can lock individual users down to particular things. But yeah, effectively at the minute it's a super user interface in that sense. Sorry, can you repeat the question? Yep. So the question was, how do things generally translate through to Mazeus? And I think, probably the answer to that is that the Kubernetes deployment itself is completely is isolated within its own thing, right? So, whatever's happening within Kubernetes is just happening within Kubernetes. You have network pathways externally from applications running in Kubernetes or applications running natively in DCOS can talk to each other. But anything you do in Kubernetes is exactly the same as you would do it in Kubernetes anywhere else. Yeah, exactly, yeah. I mean, the really cool stuff that's coming in the next releases of the Kubernetes framework is being able to do, at the minute we only run a single Kubernetes cluster within a single DCOS cluster. The next release, which is in about 2 weeks, will have the beginnings of running multiple Kubernetes clusters within a single DCOS cluster. And the aim of that in another couple of versions' time will be actually bin packing them. So you'll be able to have, effectively kubelets from different Kubernetes clusters packed into the same DCOS agents. It's actually quite a complex problem because of the ports at the minute, but that's the end goal, because that's what we see from users that folks really want to do because of this thing of wanting to run multiple Kubernetes clusters.
Any more questions?
You had a 13 in your slides. You had a slide where you had various images that were supported, including Elasticsearch.
Yeah.
And you said something like this is officially supported by Elastic.
Well, a lot of those packages are created by the companies who produce that software. Ah, well, that's okay. We can take that offline.
No, I'm just wondering because we have the same with Docker Hub, where it's official, but we're not involved in those at all.
Perhaps we're doing them in-house for that particular one. I mean, I know for things like Kafka, Confluent actually made that package.
No, I'm keep them. We were happy to have them out. It's just like we're always keep going on if we're involved or not. Otherwise, like people come to us to complain about stuff if we're not involved.
I mean, I think you're actually a partner of ours, so.
Okay, we can.
All right then. Thank you very much, Matt, for giving us these insights.
Thank you.
Thanks for being here.